In this lecture, we are going to study about the chi-square distribution. Sampling distribution of some important statistics allow us to learn about the parameter of the population. So the parameters of the populations can be inferred by the statistic of the sample we are going to study. For example, if an engineer is interested in the population mean resistance of a certain type of a register, then we are going to study the sampling distribution of means. On the other hand, if the variability of the resistance or the variance of the resistance of the resistor needs to be studied, then we are going to consider the sampling distribution of variances. Based on these statistics, either mean or the variance of the sample, we are going to infer about the mean or the variance of the population. Suppose S square is the variance of the random sample. So this is the variance of a random sample of size n. This sample is taken from a normal population having the variance sigma square. So this sigma square is the variance of the normal population. Then the statistic chi-square equals n minus 1 times s square over sigma square, or it is equals to summation x minus x bar the whole square over sigma square, is said to have a chi-square distribution. And the probability density function for this chi-square distribution is given by f of chi-square equals 1 over 2 to the power of n minus 1 over 2 gamma of n minus 1 over 2 e to the power of minus chi-square over 2 chi-square to the power of n minus 1 over 2 minus 1, where chi-square lies between 0 and infinity. Suppose that in a random experiment, a set of events E1, E2, so on till En are observed to occur with the frequencies f1, f2, so on till fn. According to a theory based on probability rules, suppose that the same events are expected to occur with frequencies E1, E2, so on till En. Then the frequencies f1, f2, so on till fn are called the observed frequencies, and the EIs are called the expected or theoretical frequencies. Let us define the statistic chi-square through the following formula, where chi-square is equals to f1 minus e1 whole square over e1 plus so on till fn minus en the whole square over en, or in short, this is summation k is equal to 1 to n of fk minus ek the whole square divided by ek. If n is the total number of frequencies, then it is expected that the summation of all the k's, where k is equal to 1 to n, should be equals to summation of all the E case, where again k is equal to 1 to n to be equals to n. If the expected frequency or at least EIs are at least equals to 5, it can be proved that the sampling distribution of the statistic chi-square is approximately identical with the probability distribution of the variate chi-square, whose density function is given as P of chi-square equals P naught chi to the power of mu minus 2 e to the power of minus chi-square over 2, where nu is a positive constant called the degrees of freedom and P naught is a constant depending on nu, such that the total area under the corresponding probability curve is 1. The number of degrees of freedom nu is determined by the formula nu is equals to n minus m, where n is the number of frequency pairs, frequency pairs fi comma ei, and m is the number of quantities that are needed in the calculation of ei. In practice, the parameters of the population are computed on the basis of the null hypothesis H naught. If under this hypothesis the value of the chi-square computed with the use of the formula is greater than some critical value chi-c square, we would conclude that the parameter differ significantly and we are going to reject the null hypothesis at the corresponding level of significance C. Otherwise, we would be accepting it or at least not reject it. This procedure is called the chi-square test of hypothesis or chi-square test of significance. Generally, the chi-square test is employed by taking C equals 0.05 or 0.01. Next, let us talk about the goodness of fit. When a hypothesis H naught is accepted on the basis of the chi-square test, we say that the expected frequencies calculated on the basis of H naught form a good fit for the given frequencies. When H naught is rejected, we say that the corresponding expected frequencies do not form a good fit. Now let us consider some problems on the chi-square test. Here's the first problem. A manufacturer of car batteries guarantees that the batteries will last an average 3 years with a standard deviation of 1 year. So the population mean is given, which is 3, and the population standard deviation is given, which is 1. Assuming the battery lifetime follows a normal distribution, find chi-square for the lifetime 1.9, 2.4, 3.0, 3.5 and 4.2 years of 5 of these batteries. So here these are the X values given and the number of batteries we are testing is 5. Test the hypothesis at 0.05 level of significance given the chi-square at 0.05 level of significance with 4 degrees of freedom as 9.49. So from these x values we can calculate x bar, which is the sum of these values over the number of samples we have considered, which is 5, which gives the value to be equals to 3, and s square would be equals to 1.9 minus 3 square plus 2.4 minus 3 square plus 3.0 minus 3 square plus 3.5 minus 3 square plus 4.2 minus 3 the whole square, everything divided by n minus 1, which is equals to 4. And we see that it is equals to 0.815. So this is s square. So we can calculate the chi-square using the formula n minus 1 s square over sigma square, which is 4 times 0.815 over sigma is 1. So 1 square is 1, which gives us 3.26. So we do want to compare this 3.26. That means if it is greater than, so greater than the chi square, which is chi square 0.05 of 4, which is 9.49. So we do see that 3.26 is not greater than 9.49. So therefore we are going to accept the hypothesis. Let us consider the next problem. It reads, a maker of a certain brand of a low-fat cereal bars claims that the average saturated fat content is 0.5 grams with standard deviation of 0.2 grams. So therefore these will be our mu 0.5 and sigma is 0.2. In a random sample of 8 cereal bars, so that is n is equals to 8. This brand saturated fat content was 0.6, 0.7, 0.7, 0.3, 0.4, 0.5, 0.4, 0.2. So these are our x values. Would you agree with the claim that is mu equal to 0.5 and sigma equals to 0.2 at 5% level of significance, given the critical chi-square value at this level of significance and 7 degrees of freedom to be equals to 14.07. So x bar would be equals to 0.6 plus 0.7 plus so on 0.4 plus 0.2 divided by 8, which is found to be equals to 0.475, and s square would be equals to 0.6 minus 0.475 the whole square plus so on till 0.2 minus 0.475 the whole square divided by n minus 1, which is 7, and it is found to be equals to 0.0336. So chi square would be equals to n minus 1 s square over sigma square, which is found to be equals to 7 into 0.0336 over 0.2 the whole square, and it is found to be equals to 5.88. So here we're going to compare this 5.88 with chi square 7 at 0.05 level of significance, which is equals to 14.07. So here we want to check whether it is greater than, and it is not certainly greater than. So we are going to accept the hypothesis. The next problem is consider the following measurements of the heat producing capacity of the coal produced by a mine. Those reads as 8260, 8130, 8350, 8070, 8340. Can it be concluded that the heat producing capacity of that mine has a standard deviation of 130? That is, sigma is given to be equals to 130. So we do want to test this claim. So use 1% level of significance given chi-square at 0.01 level of significance with 4 degrees of freedom to be equals to 13.28. So here x bar would be again 8260 plus 8130 plus 8350 plus 8070 plus 8340 over 5. So this is found to be equals to 8230, and your s square is equals to 8260 minus 8230 the whole square plus on 8340 minus 8230 the whole square divided by 4, which is found to be equals to 125.499 the whole square, and the chi-square would be equals to n minus 1, which is 4, s square 125.499 the whole square divided by sigma square, which is 130 square, and it is found to be equals to 3.7278. And here we are going to compare this 3.7278 with chi-square 0.01 of 4, which is equals to 13.28. We do want to check whether it is greater than. So here, since 3.72 is not greater than 13.28, we are going to accept the hypothesis. That is, the heat producing capacity of that mine has a standard deviation of 130. The next problem is, in 200 tosses of a coin, 118 heads and 82 tails were observed. Can the coin be considered fair? Given chi-square 0.05 of 1 equal to 3.84. So we know that if H0 is accepted on the basis of the chi-square test, we say that the expected frequencies calculated on the basis of this H0 form a good fit, or else it's not a good fit. So here, if H0 is accepted, it would be a good fit, then the coin would be fair. So we are going to test this hypothesis. So here our frequency of occurrences or with respect to the head, which is 118. So our F1 will be 118, and the frequency of occurrence of the tails is the second frequency, that is F2 is equals to 82. In general, if I toss a coin one time, the probability of getting a head would be half, but here we are tossing 200 times. So therefore, the expected frequency of getting the head out of 200 tosses will be even. And similarly, the expected frequency of getting tails out of 200 tosses would be 200 times 1 by 2, which is 100 and 100. So now let's calculate the chi-square using the formula F1 minus E1 the whole square divided by E1 plus F2 minus E2 the whole square divided by E2, which is 118 minus 100 the whole square divided by 100 plus 82 minus 100 the whole square divided by 100, which is found to be equals to 6.48. And we do want to compare this 6.48 with chi-square 0.05 of 1, which is 3.84. So certainly this 6.48 is greater than 3.84. So we are going to reject the hypothesis. And what was our hypothesis? H0 was it's a good fit, the coin is fair. So we are rejecting the hypothesis, that is the coin is not fair. The next problem is, a dice is thrown 60 times and the frequency distribution for number appearing on the face of the dice is given by the following table. they're asking you, is the dye unbiased? And the critical chi-square value is given as 15.09 at 0.01 level of significance and 5 degrees of freedom. Okay, so here if I take the sum of all the frequencies, it is found to be equals to how much? 15, 25, 32, 42, 52, 60. Okay, so if I throw a die once, the probability of getting 1 is 1 over 6. So out of 60 it would be 10. Similarly, probability of getting a 2 would be 1 out of 6 into 60, which is again 10. So these becomes our expected frequencies. So E for x to be equals to 1 is 10, 2 is 10, 3 is 10, 4 is 10, 5 is 10, as well as for 6 it is also 10. So now let us calculate the chi-square. So chi-square would be equals to summation of fi minus ei the whole square divided by ei, which gives us 15 minus 10 the whole square over 10 plus 6 minus 10 the whole square over 10 plus 4 minus 10 the whole square over 10 plus 7 minus 10 the whole square over 10 plus 11 minus 10 the whole square over 10 plus 17 minus 10 the whole square over 10, which is found to be equals to 13.6. So this is the calculated chi-square value. So here they're asking you to find whether the die is unbiased. So here our if you are going to accept the null hypothesis, then we say that it is a good fit. That means the die is fair, or in other words we say that it is unbiased. So here if we compare this calculated chi-square with the critical chi-square value, chi-square 0.01 of 5, which is 15.09, we do see that it is not greater than 13.6 is not greater than 15.09. So we are going to accept the null hypothesis. That is, we can say that the die is unbiased. So that is, die is unbiased. The next problem reads like this. Genetic theory states that children having one parent of blood type M and other of blood type N will always be one of the three types M, Mn, N, and that the proportions of these types will on an average be 1:2:1. A report states that out of 300 children having one M parent and one N parent, 30% were found to be of type M, 45% of type Mn, and the remaining of type N. Test the theory by chi-square test. Given chi-square 0.05 of 2 equals 5.99, chi-square 0.01 of 2 equals to 9.21. So first let us look at what would be the observed frequencies. So they are saying that out of 300 students, 30% were found to be M, 45% Mn, and remaining means it would be 25% or type N. Okay, so the observed frequencies or 30%, 45%, and 25%. So blood type of M is 30% of the 300 children, so which gives 90. So this is our F1. Type Mn is 45%, so 45 over 100 into 300, that gives us 135, which is F2. And type N is 25%, so that gives us 75, so this is F3. But they're expecting to have these blood types in the ratio of 1:2:1. So the expected frequencies are in the ratio of 1:2:1. So type M is expected to be 1 out of, so if I add all these ratios, it will add up to 4. So out of 300, how much is this? So which is 75. This is our even. Type Mn would be 2 out of 4 into 300, which is 150, which is E2. And type N is 1 out of 4 into 300, again it is 75, which is equal to E3. Okay, so now let's calculate the chi-square. So chi-square is given as summation of Fi minus Ei the whole square divided by Ei. So on substituting, we will have F1 90 minus 75 the whole square divided by 75, plus 135 minus 150 the whole square divided by 150, plus 75 minus 75 the whole square divided by 75, which gives 4.5. So here we are supposed to compare this with the chi-square of 0.05 of 2, which is given to be equals to 5.99, and we are supposed to compare this with the chi-square 0.01 of 2, which is given to be equals to 9.21. So here you see that 4.5 is not greater than 5.99, so we are going to accept the hypothesis. And 4.5, again it is not greater than 9.21, we are going to accept the hypothesis. So in fact we are going to accept the hypothesis both at 5% and 1% level of significance. That is, we can state that the genetic theory seems to be correct. The next problem is over the years the grades in a certain college professors class are typically as follows: 10% A's, 20% B's, 50% C's, 15% D's, and 5% F's. The grades for her current class of 100 are 16 A's, 28 B's, 46 C's, 10 D's, and 0 F's. Test the hypothesis that the current class is typical by a chi-square test at 0.05 level of significance, given chi-square 0.05 of 4 equals to 9.49. Okay, so here first let us see what are the observed frequencies observed or for the current class. So it is observed that there are 16 A's, 28 B's, 46 C's, 10 D's, and 0 F's. So these are the observed frequencies. So these will be our F1, F2, F3, F4, F5. But for a typical class, the expected values or the expected frequencies are 10% A's. So here if I add, the total is equals to 100. So summation f equals to 100, and here it is again given in terms of the percentage. So summation e is also equals to 100. So here expected that there should be 10% or 10 A's out of 100, 20 B's, 50 C's, 15 D's, and 5 F's. Okay, so these will be our expected frequencies: E1, E2, E3, E4, and E5. So the chi-square will be again summation Fi minus Ei the whole square divided by Ei, which gives 16 minus 10 whole square over 10 plus 28 minus 20 whole square divided by 20 plus 46 minus 50 whole square divided by 50 plus 10 minus 15 the whole square divided by 15 plus 0 minus 5 the whole square divided by 5, and it is found to be equals to 13.79. And we are supposed to compare this with the chi-square at 0.05 level of significance and 4 degrees of freedom, which is equals to 9.49. And here we see that 13.79 is indeed greater than 9.49. So we are going to reject the hypothesis. Okay, so the null hypothesis would be the class is typical. We are rejecting the null hypothesis, that is the current class is not typical. The next problem is to fit a binomial distribution to the following data and verify whether it is a good fit. So here the x and f values are given. So these are the observed frequencies. So we need to fit a binomial distribution. So let us find the mean for the binomial distribution, where mean is given as summation fx over summation f. Summation fx would be 284, summation f is 100, so this gives mu to be equals to 2.84. So we are expecting to fit a binomial distribution. So the relationship between the mean number of trials and the probability of success is mu is equal to np, which implies p equals to mu divided by n, or 2.84 divided by 5, which is 0.568. From this we can obtain q, which is 1 minus p. So we will have q as 0.432. So the normal distribution function is given as ncx p power x q to the power of n minus x. We know what is n. We need the number of trials here, it is 5. So it will be 5 cx p is 0.568 to the power of x, and 0.432 to the power of 5 minus x. So this gives, these values gives only for 1. So this if I substitute x equal to 0, that will be the probability of x equal to 0, which is expected to be less than 1. But we need the frequencies, and we need to calculate the frequencies over with respect to 100 number, because summation f is equals to 100. So we will be multiplying this function with a 100. So this will be our expected frequencies, which are the EIs. So when x equals to 0 in this function, E1 would be equals to 1.50. On substituting x equals to 1, we will get E2 to be equals to 9.89, E3 is 26.01, E4 equals to 34.20, E5, while substituting x equals to 4, is 22.48, and E6 equals to 5.91. So we will approximate these frequencies to the nearest whole number. So these will be approximated to 2, 10, 26, 34, 22, and a 6. So these are our EIs, and our observed frequencies are 2, 14, 20, 34, 22, and 8. So in order to apply the chi-square, we need the frequencies to be at least 5. So here we observe that one of the frequencies is not 5, it is less than 5. So here what we will be doing is we will be clubbing these two frequencies. We will be clubbing these two frequencies. So the new IIs are 12, 26, 34, 22, 6. So these are the expected frequencies, and the new observed frequencies are 16, 20, 34, 22 and a 8. So now we can calculate the chi-square, which is summation fi minus ei the whole square divided by ei, which is 16 minus 12 whole square over 12 plus 20 minus 26 the whole square over 26 plus 34 minus 34 the whole square over 34 plus 22 minus 22 the whole square over 22 plus 8 minus 6 the whole square over 6, and the value is obtained to be equals to 3.38. Okay, so this is the calculated chi-square value. So here the new frequencies are how many? 1, 2, 3, 4, 5. So we have 5 data points available to us, that is n equals to 5. But here in order to fit the binomial distribution, we have used two parameters. One is mu and the other one is x. So therefore the degrees of freedom will be equals to number of data points, which is 5, minus of the parameters which we have used to calculate the binomial distribution. So it is 2, which gives us 3. And chi-square at 0.05 level of significance and 3 degrees of freedom, it is 7.815. So we are going to compare 3.38 with 7.815, and we see that 3.38 is certainly not greater than 7.812. So we are going to accept the hypothesis. Accept the hypothesis. The hypothesis is it is a good fit. Whatever we have fitted the binomial distribution. So in other words, it is a good fit.